Okay, today we will see Cascode amplifiers. But before that, just a quick reminder that we had seen in the last class the different hybrid parameter equations. Okay, and what is the use of hybrid parameter equation in modeling a BJT? And then I gave a simple or typical values for these different H parameters in a tabular form. Okay, just to have an idea about the typical values that these parameters can assume for a common emitter amplifier, common emitter BJT. And these are the values for the transistor number 2N4400. Okay, and then we saw the different equations that is there, and we know that there are four parameters that are important for an amplifier, and those are the input resistance, then output resistance, then voltage and current gain. Okay, then current gain and output resistance. And we also analyze the dependence of these different parameters on the H parameters. Okay, and the task was to compare these parameters with a single stage emitter follower. Then there were some limitations, some demerits of these. The most important ones is that it is a slow switching speed. It operates a bit slowly. Okay, the bandwidth is limited in this case, and since this is a connection of two back-to-back BJTs, so it requires for turning these BJTs on, we require at least 2 times the value of the voltage VBE. Okay, 2 VBE. And so and also the saturation voltage is high for this case, so that will lead to a more power dissipation, and also it requires a higher value of voltage to turn it on. Okay, so these were the points that are there for this particular circuit, Darlington pair. These are the cases for Darlington pair. Okay, and the next topic that we would see is called as Cascode amplifier. Okay, look at here. What is basically this is again a two-stage amplifier. So there are two stages connected back to back. Okay, so basically a common emitter stage is connected in series with a common base stage. Okay, so this we know that is a simple common base BJT, common base BJT NPN transistor. Okay, this is the input voltage and this is the load resistance across which the output voltage will be taken. And this is a simple common emitter BJT. The emitter is common between the input and output sides. Okay, and when we connect these two that is when first stage is made by the common emitter. Okay, this one comes here, common emitter, and the output of common emitter, that is this output is connected to the input of common base, the base is common. Okay, and then the output is taken across at the output of this common base. Okay, so basically this common emitter is connected in series with this common base, and this particular configuration is known as a cascode configuration. Okay, sorry. Okay, so and the input voltage will be applied at the input of the emitter, common emitter stage. Okay, the first stage, and the output will be taken at the output of the second stage, that is common base stage. Okay, so this is again a simple configuration termed as cascode configuration, and in the book they have given this diagram. Let us have a look at this. This is the first stage. Okay, look at here. Common emitter, the emitter terminal is common. okay, between input and output. Okay, and this is the base of this Q1 transistor, Q1, where the input signal is applied. This is the input signal, voltage signal, and this is the internal resistance of the source of the source Vs. Okay, so these two form the input signal source. Okay, and the output of this Q1, that is this collector, is connected to the input of this common base. The base terminal is made common, is coming here down, and the input is taken. This input emitter terminal is connected to the output of this Q1, that is collector. So this output of Q1 is connected to the input of Q2, and the output of Q2, that is this collector terminal, is brought here, and one load resistance is connected here. Okay, and the output voltage is measured across this load resistance. This is our V0 or V2. Okay, and this voltage across this terminal, this base terminal and ground, is Vi or V1. Okay, basically because there would be some voltage drop across this resistance Rs, so the potential at this point would be a bit lower than Vs. Okay, let us say that this potential is Vi or V1, and at the output side, let's say this is V0 or V2. Okay, and these terminal where this is the output of Q1 and input of Q2. Okay, let's say this is some VR, some potential VR. Okay, and the biasing voltages are not shown here. Okay, only the input voltage is shown here. So assume that a proper biasing mechanism is provided to these transistors. Okay, because we know that without biasing we cannot use transistors to as an amplifier, or for the case for any switching purpose or amplification purpose, a proper biasing has to be provided. Okay, again now let us go to the H parameters for this cascode amplifier. The first parameter is H11. So if you recall, the H11 was the input resistance. Okay, I for input resistance. Okay, and by definition it was the ratio between V1 and I1, and provided that I2 is equal to 0, that is the output terminal is made as open circuit. Okay, now if V2 is 0, then the load of Q1 is simply HIB2. Okay, which is extremely small, being only about 20 ohm. Then load of Q1 is simply HIB2, that is load of Q1 is simply HIB2. If basically this should be that this should be I2 0, because we are satisfying this condition, I2 0. Okay, so it means that if I2 is 0, that means this terminal is open circuited. We have not connected any load resistance here. This RL is infinite. So in that case, what happens? The load of Q1, that is the load of Q1, that is the load at its output terminal, becomes the input resistance of Q2 is basically equal to the input resistance of Q2. Okay, so this is what is said here, that when I2 is equal to 0, then the load of Q1 is simply HIB2, where HIB2 is the input resistance parameter for B for common base. Okay, for common base second stage. Okay, so it is simply saying that the load of Q1, when you look from this angle, the load of Q1 becomes equal to the input resistance of Q2, because this is the input terminal for Q2 and also this is the output terminal for Q1. Okay, and what is the input resistance for Q2? That will be defined by the parameter HIB2, because this is a common base stage. Okay, and second stage, so HIB2. Okay, and we know that the input resistance of a common base configuration is low, very low. And why it is low, let us see. Okay, so this terminal is open circuited, and I want to calculate the resistance that is seen when we look from this side. Okay, what is the input resistance? Okay, this particular terminal is open circuited, and this particular terminal uh, is uh, forward bias, sorry. Okay, so this particular junction is reverse biased, we know that thing, and this particular junction is forward biased. Okay, so this is reverse bias. Okay, reverse bias means a kind of open circuit. Okay, and forward bias means a kind of short circuit. Okay, so if you look from the input side, what you will see that this particular junction is, this particular terminal is a kind of open circuited, and this particular junction is kind of short circuited. So we can say that if some current has to be has to flow, it will flow in this branch. Okay, and go to the ground, and whatever this branch offers, whatever resistance this branch offers would be the input resistance for this particular q2 when it is seen from this side. Okay, and this is a forward bias junction, and we know that the resistance of a forward bias junction is very low, of the order of few ohms particularly. Okay, so it may be around 10, 15 or 20 ohms, and this is what is said here, that is HIB2 input resistance is extremely small. Okay, being only about 20 ohm. So it means that the output, that is the load of Q1 is around just 20 ohm, and 20 ohm is a very low value of resistance. So we can say that Q1, the first stage transistor, is almost short circuited. That is, if this branch, if okay, now we know that this particular branch is offering just a 20 ohm of resistance, so it means that the output terminal of Q1 is connected to a load of around 20 ohms. Okay, so it means that the load connected at the Q1 is just around 20 ohms, and 20 ohm is a pretty low value, so we can say that the output terminal of Q1 is a kind of short circuited, because we can neglect this 20 ohm, we are neglecting this 20 ohm. Okay, so this is what, thus the transistor Q1 is almost short circuited. Okay, and hence H11 becomes HIE, H11 becomes HIE. Okay, now the short circuit current gain of the circuit is given by S21. By definition, S21 is the ratio between I2 and I1. This is provided that V2 is connected to 0. So this is forward current gain when output is short circuited. Okay, and we can multiply in the numerator side by IR, in the denominator by IR. And what is this IR by I1? Look at this. This is IR, and this would be I1. So this IR by I1 is the forward current gain for Q1. Okay, and there would be another ratio that would be between I2 by IR. Okay, and I2 by IR becomes the forward current gain ratio for Q2. Okay, so this is IR by I1 and I2 by IR. Okay, and IR by I1 is HFE, the forward current gain ratio for common emitter E, and I2 by IR is HFB, the forward current gain ratio for common base transistor. Okay, and there is a negative sign uh, because here IR is entering into this Q1, fine, but at the same time IR is coming out from Q2. Okay, so generally we assume that at the input side this enters into the input terminal, but this is coming out, so because of this a negative sign is taken here. Okay, but HFB is equal to alpha. HFB, the forward current gain for common base. Remember, this is a common base configuration, and what is the forward current gain for this is I2 by IR. What is I2? I2 is collector current. What is IR? IR is emitter current, and we know that collector current by emitter current is a parameter alpha, and the value of these two currents are almost equal, and the value of alpha is almost unity. Okay, so this HFB becomes 1 here, so, and hence the H21 becomes equals to HFE. HFE. Okay, so H11 is calculated here, H21 is coming out here. Now H22, what was H22? Remember, H22 was the ratio between I2 and V2, that is output current by output voltage. Okay, and basically this is output conductance. Provided that input current is 0, provided that input terminals are open circuited. Okay, now when I1 is 0, what happens? When I1 is 0, it means that the input current is assumed to be 0, so this particular terminals are assumed to be open circuited, so we have not applied any signal at the input terminal. Okay, this is just open circuited. So what happens when I1 is 0? The output resistance of Q1 is equal to 1 by HOE. Okay, HOE was what was HOE parameter? The output conductance. Okay, and the inverse of HOE would be the output resistance. Okay, right? So the inverse of I2 by V2 would be the resistance. Okay, V2 by I2, the output resistance. So this is what it is saying, that with I1 equal to 0, the output resistance of Q1 is equal to 1 by HOE. Okay, and for the case of this common emitter stage, these values are typically about 40 kilo ohms. Okay, so and this 40 kilo ohm resistance constitutes the source resistance for the transistor Q2, because we know that the output resistance of Q1 now becomes the input resistance for Q2. Okay, the output resistance of Q1 acts as a load for Q2. Okay, so this is what it is saying, that this 40 kilo ohm resistance constitutes the source resistance for the transistor Q2. Okay, and it may be shown that for Q2 in common base configuration, the output resistance R2 with source resistance Rs of 40 kilo ohm is almost the same as that for Rs is equal to infinity. Okay, and we get the value of R0 equals to 1 by HOB. HO is again the output conductance. Okay, and inverse of HOB becomes the output resistance, and hence the H22 is equal to 1 by RO, that is equal to HOB. Okay, so try to recall these different H parameters and the characteristic of common base, common emitter, transistors. Try to recall these things from your earlier subjects. Okay, because here they have not gone into much depth, but rather they have given the direct equations for all these parameters. Okay, so because this is a bit this you are studying in 7th semester, so it is assumed that you are aware of the earlier concepts. Okay, now the H12 parameter, that is the ratio of V1 by V2 provided that I1 is equal to 0. Okay, and again we can multiply in the numerator and denominator by VR, so it becomes V1 by VR and VR by V0. Again let us see, so V1 by VR is the reverse voltage gain for Q1. Okay, V1 by VR, and VR by V2 is the reverse voltage gain for transistor Q2. Okay, and for common emitter this becomes HRE, and for common base it becomes HRB. Okay, and so H12 becomes multiplication of HRE with HRB. Simple, straightforward. Okay, and this is given in the section 18.4 in the book Mithal and Gupta. Okay, so you can read this section from that particular book, Manisha Gupta and J.K. Mithal and Manisha Gupta. Okay. So these are the four parameters for the Cascode amplifier, and uh, you note down one more point here, one more task here, just since because this is related to common Cascode amplifier. So write down the important characteristic of a Cascode amplifier. Note down in your in your uh, copies the characteristics characteristics of Cascode amplifier. Okay, so take it as a problem, take it as a homework problem, and try to find out the points, the characteristic. Okay, now this characteristic will include all the points that may be taken as a merit point or a demerit point. So those may be an advantage or a disadvantage, whatever. But so it means I mean to say that what are the important points, what are the important characteristic regarding this Cascode amplifier. So those points may be may look like a advantageous point or may look like a disadvantageous point. It doesn't matter, but we should be aware of that what are the positive points of this amplifier and what are the negative points about this amplifier. Okay, we should be aware about this. So take a note of this this problem. Okay, and I have given here just for your convenience uh, the comparison between common base, common emitter, and common collector. Okay, so let's start with the first. Let's say, for example, voltage gain. We know that voltage gain in the case of common base is high, and common emitter is also high, and in the case of common collector, it is unity. Actually, less than unity. Okay, the current gain is in the case of common base, the base is common, the output is collector, the input is emitter. So we know that the collector current is lower than emitter current, so it is somewhat less than unity. Okay, so it is alpha actually. And in the case of common emitter, since emitter is common, okay, output is collector current, input is base current, and collector current is very high, so current gain for common emitter becomes very high, and for common collector similarly is high, because output is emitter current and input is base current, so it becomes naturally high. Okay, the power gain, and hence the power gain is actually the multiplication of voltage gain, okay, and the current gain. So when you multiply these two, you get power gain. So power gain in the case of common base is of moderate value for common base, and since in the case of common emitter this is also high and this is also high, so you get the highest amount of power gain in the case of common emitter configuration. Okay, and it is moderate for the case of common collector configuration. Right, next, phase inversion. Phase inversion means the relation between the phase change between the input and output signal, and we know that in the case of common base there is no phase inversion. In the case of common collector also there is no phase inversion, but there is a phase inversion of 180 degree between output and input current in the case of only common emitter. Okay, and input impedance and output impedance. Input impedance for common base is low. uh, it would be around less than equal to 50 ohm, okay, because base is common, input is emitter. So at the input side you will see that particular forward bias junction, okay, the forward bias junction, and the resistance of forward bias junction is low, very low. Now common base, common emitter, it is around it is of moderate value, and it is around 1 kilo ohm, okay, and it is very high, it is high of the order of 300 kilo ohms in the case of common collector, okay. And output impedance in the case of common base is high of the order of 1 mega ohm, and it is of moderate value of the order of 50 kilo ohms in the case of common emitter, and in common collector, but it is low, around 300 ohms. So these are just typical values for the three configurations, and keeping in mind these typical values will help you in understanding the particular BJT and its amplifier, the related amplifiers, with more clarity. Okay. Okay. Again, this is a parameter. This is a This is a table that is comparing those three uh, 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 common emitter, common base, and common collector amplifiers. And this is again the same table, but here the values are given in terms of the parameters, okay, in terms of beta Re, where Re is the thermal resistance, okay, Re is the thermal resistance, beta Re is the, I think, the resistance connected at the emitter terminal, okay, then Rc, the resistance connected at the source, at the collector terminal, okay, and this small Re is the thermal resistance. Then RL by RL is the load resistance, Re is the thermal resistance, and beta is, we know the beta is the ratio between IC and IB. So just go through this table, okay. This table is similar to this table. The only thing is that here we have here only the indications are given whether they are high or low, but here uh, some values, indications are given, okay, and along with the actual values in terms of the parameters, okay. Okay, so with this the cascode amplifier stage is over, okay.